Welcome. In this lecture, we are starting the secondary steel making, and this lecture will it is on introduction and deoxidation. Okay, that is the introduction of secondary steel making and deoxidation. Concept covered will be importance of secondary steel making, why secondary steel making is important, and then deoxidation thermodynamics, deoxidation kinetics, and how to measure the dissolved oxygen probes, and deoxidation practices, how we carry out the deoxidation practice in steel plant. Okay, first let us talk about the significance or importance of secondary steel making. So, basically the secondary steel making came, now today it has come. This is the major reason, the special grade of steel with ultra low impurity tolerance that is required today, because nowadays the more demand are coming for very ultra low impurity steel, especially ultra low carbon steel, ultra low sulfur steel, and where the impurity concentration may be required below 50 ppm, like sulfur below 50 ppm and carbon below 50 ppm, like that. So, those are called. So, those type of steel is usually impossible to make under primary steel making unit like LD process. And as we have shown you, that is carbon can be reduced maximum to a level of around 200 ppm under 1 atmospheric pressure. If you want to go down below that, then you need vacuum. So, secondary steel making offers those possibility. So, even sulfur, if you want to remove to a very low level, you have to treat it with synthetic slag under stirring condition, bath stirring condition, and that is also possible under secondary steel making. And also you have to make very ultra low impurity, that is ultra low gaseous impurities like nitrogen and hydrogen. Okay, those also has to be very low for subsequent operation, because some steels are there where for deep drawing purpose, if you want to make a steel where nitrogen should be very, very low. So maybe less than 50 ppm. So, to make those steel kind of steel, we need vacuum treatment. Not only that, we have to deoxidize, and deep deoxidation and deep desulfurization is required before denitrogenation, and that is possible only under secondary steel making. So, that is the most important why secondary steel making came. That was the one of the major reason, that is the special grades of steel with very stringent impurity control is coming nowadays. So, customer demand is coming with a very special grade of steel. That is one reason. And obviously, another is the secondary, that is the higher productivity. Basically, now what we do, because in the primary steel making unit like LD furnace, there we can produce steel in 45 minutes. So, we are just concentrating on producing as fast as possible the steel under primary steel making unit. There we are basically producing a mild steel, that is the low carbon steel of the order of, say, more than 100 ppm, that is the more than 200 ppm steel we can produce under LD steel making, and we can make those steel, low carbon steel, as quick as possible. That is the crude steel we produce under the primary steel making unit, because then after the liquid is poured into the ladle, then the ladle will move from tapping ladle will move from the SMS to the caster. So, during also when this movement, there is also a lot of time is there, and there we can make further processing of steel to the requirement of the customer, and then we can use that time, that is this transit from SMS to the caster, we can utilize that time for different secondary processing. That way we can save also a lot of time, and we can increase the productivity. So, primary steel making should be as fast as possible, then processing during its transit of the ladle from SMS to the caster, and we can utilize the time that way. Okay, because several times caster is not available. So, sometimes the ladle are hold on transit. So, you can utilize that time. That way it is the productivity is also high. And then, as I said, the clean steel, very ultra low impurity steel, or sometimes that is the clean steel means you can, some of the impurities you have to live with the impurities, because there are several impurities into the steel, and we can remove them to some extent, but you have to live with the several inclusions. That is, the very fine inclusions are there in millions, and 1 micrometer inclusion, 10 micrometer inclusion, maybe in 1,000, 100 micrometer inclusion, maybe of the order of 100 or like that. So as a result, so it is clean steel doesn't mean that you can make a steel which is impurity free. So you will have to live with this inclusion, but you can modify them. So you can modify them to a certain size and shape distribution with a certain shape, such that that doesn't make difficulties in further processing of the steel. Okay, so that is called the inclusion modification. So those inclusion cannot be removed, can be modified to a with a favorable size shape distribution. Okay, that can be done, and that is called the clean steel. After inclusion modification, we can do that, such that inclusion that is remaining, that cannot be eliminated from the steel, can be modified and does not hamper the further processing of steel. And finally, the continuous casting requires the stringent quality control. Basically, it is a very fast process, continuous casting. So it doesn't allow much of the impurity to come out and bubble through this liquid. Mostly the gaseous inclusions, gaseous impurities you have. So if they form the bubbles during solidification, because of supersaturation, the gaseous bubble can form, because solid has very limited gaseous solubility, very limited solubility, where the liquid has large solubility. So there is a huge difference. So when the liquid solidify, a lot of gas supersaturation take place at the solid liquid interface, and this impurity can form the bubbles, gaseous impurity can form the bubbles, but bubbles may not get sufficient time to go away from the system, because continuous casting like this process are very fast process. So they may be entrapped, or due to supersaturation, lot of precipitation can take place during during the solidification, and these precipitates may not float up to the slag or to the top. So as a result, those will be entrapped. So that's why the continuous casting requires a stringent quality control. Basically, impurity, impurity tolerance is not high in continuous casting because of its very fast nature of solidification. So these are the basically reason which has given the secondary steel making, because primary steel making you cannot do this thing. You cannot make a clean steel, you cannot make a so very less impurity steel, and all these things suitable for continuous casting is very difficult, and you have to take the help of secondary processing of steel in ladle, that is called the secondary steel making. Okay, now there are various operations in secondary steel making, like you have now the deoxidation is also carried out in secondary steel making. When you tap the liquid steel, you can do that, or otherwise you can do the deoxidation after taking the ladle to the ladle furnace, or there are several stations where you can do the deoxidation, deep deoxidation. So deoxidation, and then you can do the degassing under vacuum in secondary steel making. You can do the deep decarbonization by oxygen blowing, you can do that. Both you can lower down the carbon and oxygen under vacuum, okay, by oxygen bottom blowing, that is called the decarbonization. And then desulfurization, you can do desulfurization by synthetic slag treatment into the ladle, then inclusion, removal and modification, just now we indicated, and then temperature and compositional homogenization. Basically, in continuous casting also, it cannot tolerate a different exit temperature of the liquid. When you are steaming the liquid steel into the caster, that is in a mold, then the liquid temperature should be uniform, because based on that a particular temperature, your heat extraction amount, everything is fixed up. So if you pour liquid at different temperature, then continuous casting cannot work, because it will not produce the proper result. So continuous casting requires a constant temperature, constant superheat of the liquid. So it cannot deal with change in the fluctuation in the superheat. So temperature within the ladle has to be uniform before the ladle is taking in the steaming station. When the liquid is poured from the ladle to the mold, it is called steaming. And when it is tapped from the LD to the ladle, it is called the tapping operation. So during the steaming operation, okay, the temperature, there is because when the ladle basically from the SMS, when it goes and stays or kept on hold for some time, then lot of thermal stratification take place, because the ladle losing the heat from the side wall from the top. So, center will be at higher temperature and near the wall will be lower temperature. So, when the liquid will come out at different temperature unless you homogenize the bath. So, before you take it to the tipping station, the ladle should be homogenized by inert gas purging. Besides, you can do lot of alloying and all these things and alloying, and so compositional adjustment, there is the compositional homogenization also important. That is why the gas stirring is required. So, gas stirring is a very important phenomenon in secondary steel making to homogenize the bath both with respect to the temperature and composition. Okay. Now, temperature compensation also, because when the ladle is going in transit, because it is losing lot of heat or sometimes, so continuous caster requires a certain amount of superheat. So, you have to maintain that superheat. So, some temperature compensation may be required, and that you can do by arcing in ladle furnace, or sometimes what is called the chemical heating by addition of aluminum, but that is not a very good approach because it introduces the inclusion. So, arcing is there in the ladle furnace, you can do the arc and you can compensate the temperature. So, those are the facilities that are available in the secondary steel making. Now, what are the units? You can see this is called the vacuum arc degassing, basically heating and degassing, because arcing is there. There you can do the heating, just compensation of heat, and degassing you can do under vacuum. This is the vacuum degassing without arcing. So, here there is no temperature compensation. This is the VD unit called degassing. And you have, this is the vacuum oxygen decarburization. So, you have to supply oxygen also such that you can decarburize the bath to a very, very low level. That is called the vacuum oxygen decarburization. Under vacuum you do, then whatever the CO evolve, that will go away. So, then it is called the vacuum oxygen decarburization, then argon oxygen decarburization. These are basically, here you can do the decarburization. And since you are giving the oxygen, you are doing some chemical heating, because of oxygen will react with the carbon forming CO and CO will go away. That is an exothermic reaction. So, you can give some chemical heating as well as you can decarburize the bath. And then you have LFs, this is called the ladle furnace. Here you do the heating and lot of things, homogenization by bottom gas stirring. You can do the desulfurization by synthetic slag, making synthetic slag, that is the basic and deoxidized reducing slag you have to make for desulfurization. You can do the deoxidation and you can do the alloying. So, all the function can be done in the LF. LF is a very versatile. And then you have another is the IM, this is the injection metallurgy. Here you can do deoxidation, desulfurization and the inclusion modification. Basically, injection metallurgy is basically you can inject the calcium powder, different types of calcium powder and different synthetic powder, synthetic slag, flux, synthetic flux also you can inject. That is called the injection metallurgy, because most of the cases you cannot dump this alloying element or this calcium powder. Basically, the calcium powder you cannot dump at the top. Thing is that then calcium will react. It is a very highly reactive and also volatile. So, you cannot just spray or you can dump the calcium powder on the surface, then it will not be utilized. So, most of the cases highly reactive and volatile material that you want to react with the steel, you have to basically inject those rather than dumping at the top. So, that is why injection metallurgy came. That is also a technique how you can inject. You can do by submerged lens injection with carrier gas this powder. Using a carrier gas, you can inject this powder through a submerged lens, or sometimes you can do it by what is called the cold wear injection. Cold wear is nothing but a hollow cylinder in which you can pack the powder and it looks like a rod wear, and then you can feed the wear by mechanical system. Okay, that is also called, and then the wear will penetrate into the bath, and where it will melt. When the wear casing melts, the powder will be released, and that is called, that is wear injection. So, there are different injection methodologies, submerge injection, or you can submerge injection by lens, or you can do by wear feeding, right. So, these are called the injection metallurgy. And another unit, that is I will come later on also, is called the RH degasser. That is also a very versatile unit, and where you can do deep deoxidation, decarburization and synthetic slag treatment, degassing. because it is equipped with the vacuum, because LF is not equipped with the vacuum, but RH unit is equipped with the vacuum also. So you can do degassing, that is the desulfurization, deoxidation, alloying very effectively. And especially RH is used for making a very microalloying steel or the deep deoxidation, deep desulfurization, all this purpose. Okay. But LF is used mostly for the homogenization, gas turbidity homogenization, then heating, and desulfurization, deoxidation, alloying you can do. But when you do on a very sophistication level, alloying, microalloying, you want to do say deep deoxidation and very, very deep desulfurization, you can take the help of RH also. So those are the units that are available in the secondary steel making unit. Now, first operation in the secondary steel making is called the deoxidation. We will talk about the deoxidation, and first of all, why deoxidation is required. You see, that is very important. That is the after oxygen steel making you have seen, that is in the turn down sample, that is when you tap the liquid steel from LD to the ladle, then if you measure the oxygen concentration in the ladle, it is around 800 to 1000 ppm. That is the dissolved oxygen you will get. So that we have told also earlier also during the LD steel making. So after oxygen steel making, liquid steel contains around 800 to 1000 ppm of dissolved oxygen, right? But this is the liquid state you can dissolve. Liquid state iron can dissolve this much of oxygen, 800 to 1000 ppm. But if you go to the solid state, if you solidify, then solubility of oxygen in solid steel is negligible, very, very less. So what will happen during the solidification? This oxygen will come out in the form of CO bubbles, right? As a result, what will happen? This CO bubble do not allow sufficient time for float up. They may be entrapped into the structure in the form of blowholes, right? Like in continuous casting, probability is more where the solidification rate is very fast. After oxygen gets supersaturated at the gas solid interface, this will form the CO with reacting with the carbon form the CO bubbles, and these bubbles may not have sufficient time to move up. So they will be entrapped in the form of blowholes. And besides, this oxygen also can react with other impurity elements like aluminum, nitrogen, forming different undesirable oxide inclusion. So during solidification, they can form some oxide. Oxygen is liberated from liquid steel. During solidification, precipitates undesirable oxide like aluminum oxide. It can react with the nitrogen. It can react with the silicon if impurity is possible. So a lot of oxide inclusions can be formed. And CO bubbles also, as I said, during solidification can form and can cause the blowholes. And then alloying of steel become impossible. Another thing is that if you want to do alloy and the dissolved steel and the steel contains 1000 ppm of oxygen, then you cannot alloy it, because whatever the alloying element are giving, most of the cases, if they are very stable oxide, most of the cases they are like manganese. If you want to make a manganese steel, it is not possible, because manganese oxide is more stable compared to the iron oxide. So if you have dissolved oxygen of the level of 1000 ppm, then manganese will be oxidized to manganese oxide and it will join the slag. So silicon steel, if you want to make, in that case also not possible. For transformer steel, you want to keep some silicon, it is not possible, because it will form the silicon oxide and go away. Anything, if you want to make a chromium steel, chromium will get oxidized to chromium oxide, join the slag. So you cannot retain any alloying element in the steel if your oxygen potential of the liquid steel is very high, that is the dissolved oxygen is very high. So it is essential to deoxidize the bath, or that is called the killing of the bath, before you add any alloying element. Okay. So alloying of steel become impossible. That's why without prior deoxidation, you have to do deoxidation before, otherwise alloying not possible. So this is the reason why you should do the deoxidation. Now let us talk about some thermodynamics of deoxidation, and this is the general reaction for deoxidation. Suppose X mole of metal M reacting with the Y of dissolved oxygen, Y gram atom of dissolved oxygen, it will form MXOY oxide. Suppose it is a very general oxides, right? Xm plus Yo is equal to MXY. And then you can write from the equilibrium constant, you can write activity of MXOY divided by activity of M and O. And then if you consider metal oxide is pure, then it is equilibrium constant is 1 by actually activity of M and activity of O, and if you represent the activity in terms of Hendian, there is the 1 weight % standard state, and if you assume the Henry's law is followed, the activity of M and activity of oxygen with respect to 1 weight % standard state will be just weight % of metal and oxygen, and then you can write this equation in this form, okay, where Km is not exactly the equilibrium constant, but it is called the constant. It is derived from the equilibrium constant, you can understand, and it is inverse of equilibrium constant, and then this solution, this is called the that is the solubility product. Okay, this is the solubility product of, or deoxidation constant, you can call it as deoxidation constant, that is Wm to the power x into Wo to the power y is equal to Km. It is called the deoxidation constant. This deoxidation constant is inversely proportional to temperature as equilibrium constant. Okay, so it is inversely minus of this thing, that is no, that is if the temperature increases, this time decreases, so Km increases. This time, this is the temperature, if it is high temperature, this will be low, so this term will be bigger. So, Km will be bigger, there is a solubility product will increase. So, this is the relation. Now, let us see. Now, if you see that deoxidant, for different deoxidant, you have, if you calculate the Km solubility constant, that is the deoxidation constant at 1600 degrees centigrade, and these from different correlations A and B are available for different oxides. And then, if you see the dissolved residual oxygen with respect to 1 weight % of metal into the bath, you have 1 weight % of metal in the bath, that is Wm if you consider 1, then what is the value of Wo? So, that is the value you can find. So, what does it mean if you use aluminum as a deoxidant? In that case, with 1 weight % of aluminum in the bath, equilibrium, the oxygen, the dissolved oxygen that will be in equilibrium with 1 weight % of aluminum in the bath is 2.93 × 10⁵ at 1600 degrees centigrade. Similarly, you can see calcium. If you consider the calcium as deoxidant, then with 1 weight % of calcium in the bath, the oxygen, dissolved oxygen that will be in equilibrium with the calcium will be 9.84 × 10⁻11. That means oxygen level will be reduced to almost 0. That is when calcium, 1 weight % calcium in the bath means dissolved oxygen almost 0. And so you can find, and silicon and manganese you can say comparatively high oxygen will be there, that is the 0.3 weight %. That means 0.3 weight % means 300 ppm, 1, 2, 3. Okay. So otherwise you can feel here the ppm is very low, 0. So, calcium, that is the, with 1 weight % calcium into the bath, dissolved oxygen will be almost 0, and next element is aluminum, there also the dissolved oxygen will be quite low, but and then silicon also quite low, manganese is 0.3. So, if you can see, that is the order according to the deoxidation power, this is the calcium is the highest power, and then followed by aluminum, silicon and manganese, and usually aluminum is used as deoxidant. Problem is that because the reason is that calcium, as I said, is a highly volatile and reactive. So, you cannot just dump like aluminum, you can dump from the top, but calcium you cannot do. For calcium, you require a special technique like submerged injection and the cold wear injection, but then also a lot of problems are there. And because the calcium has a very less recovery is also very less, because the calcium is highly volatile, it forms the bubbles and go away from the system, right. So, if you see the order, it is the calcium greater than aluminum greater than silicon and manganese. And let us see now the, so deoxidation kinetics, thermodynamics, what I say, there is the calcium effectively is very useful, but usually aluminum is used for easy handling of the aluminum, right. Calcium has a problem. So, for deep deoxidation, the calcium is used, but otherwise it is aluminum that is highly used. Silicon manganese is also used because silicon manganese has other advantage I will talk about during the kinetics. Okay. Now, deoxidation kinetics. So, if you see now, it is a very interesting diagram, it shows the evolution of dissolved and the total oxygen in liquid steel after addition of deoxidizer, and here we have added manganese. We are just in the laboratory scale experiment we have done, and then there is this reported data, and deoxidation by aluminum manganese they have studied, and they have studied how the dissolved oxygen as well as the total oxygen evolve with the time. Now you can see, so initially, so you can see as soon as the manganese is added, the dissolved oxygen suddenly there is a drop 600 to 400, and then it is decreasing. It is decreasing quite steadily, right? And then it is coming to 200 ppm also. But if you see the total oxygen, what is the behavior of the total oxygen? Total oxygen means dissolved oxygen plus oxygen that remains in the liquid bath in the form of inclusions like alumina, silica, okay. So combined oxygen, okay. So total oxygen is the total, that is the dissolved plus the combined, and you can measure the total oxygen by chemical analysis, okay. And dissolved oxygen, to measure you require a special probe called the Stokes probe. It is basically a solid electrolyte shell, okay. We will come to that, and using that probe you can measure the dissolved oxygen, and total oxygen you can measure by chemical analysis. And you can see here the dissolved oxygen go down very fast, that is within 7 minutes it has from more than 600 to 200 ppm, the dissolved oxygen has come. But if you see the total oxygen, it is dropping not that much. So 600 it has started above 600, and then after 7 minutes only 500 ppm. So you can find 300 ppm less in the dissolved oxygen. After 7 minutes it is dissolved oxygen is 300 ppm and the total oxygen is 500 ppm. 200, the dissolved oxygen is 200 ppm and your total oxygen is 500 ppm. So huge difference. What does it mean? That is, oxide inclusions are forming very fast, quite fast. That is, as soon as you add the manganese, then the dissolved oxygen react with the dissolved manganese and forming the manganese oxide. It is forming very fast. Within 7 minutes, you can see the dissolved oxygen has come down from more than 600 to 200 ppm. But the total oxygen is not decreasing. What does it mean is that you are not eliminating, you are forming the oxide, that is the MNO, but you are not eliminating the MNO from the system quickly. That is, after you form the MNO, then MNO has to move up and join the slag. Okay. So that process is taking time. That is the MNO not being able to join the slag phase as quickly as it is forming. That is, the transport of MNO from the liquid bulk to the slag is not very fast compared to its formation. So it is a very slow process. So manganese oxide is not rising up so quickly as compared to its formation. So that's why this is called that is, you can say, that is the rate controlling step. The inclusion formation is very faster, but inclusion removal is rate limiting. Removal means that is the transport of MNO from the bulk to the slag is rate limiting. That is, when the MNO will reach the slag, then only it can join the slag and get removed from the system, that is from the liquid metal. So you can see deoxidation kinetics, it is the removal of the inclusion is rate limiting. That is, we have to concentrate on the removal. Formation is very fast, but removal is the problem. So let's see what are the steps. Deoxidation kinetics continued. What we can do, that large particle floats up much faster compared to the smaller particles. So if I want to float the inclusion faster, what I have to do? I have to make a bigger inclusion, because bigger inclusion floats much faster compared to smaller inclusion. You can see simply the Stokes Law. Stokes Law say that is the terminal velocity, the velocity at which the inclusion will rise up is directly proportional to the diameter square. So you can find, so it is not directly not proportional, terminal velocity not proportional to d only, it is proportional to d square. That's why the problem. So you can see we have made some calculation. If you see, if the inclusion has to rise a height of 1 meter, there is a height rise of 0.1 meter or 2 meter, two cases are there. There is the height, that is the inclusion has to traverse. I have taken two cases, 0.1 meter, 0.1 meter or 2 meter, 2 meter, and I have taken diameter inclusion also. I have taken a 5 micrometer and 50 micrometer, two types of inclusions. Okay, then let's see what are the time required by the Stokes law. So if the inclusion has to traverse a distance of 0.1 meter, a 5 micrometer inclusion will take 150 minutes to rise to the slag. Compared to if you have the same height, right, 0.1 meter, suppose your inclusion size now increases to 50 micrometers. So 50 micrometer inclusion will only take 1.5 minutes. So 50 micrometer inclusion will take only 1.5 minutes compared to 5 micrometer that will take 150 minutes. That is around 100 times more, because you have increased the diameter by 10 times. So obviously the residence time will increase by the 100 times, right. So similarly, for example, 2 meter height, if you say 2 meter height, then 5 micrometer, the 50 micrometer inclusion will take only 30 minutes, where 5 micrometer inclusion will take 3000 minutes. So here 100 times. So you can see that is the larger particle will float up much faster compared to the smaller particle. So we have to see how to make the particle bigger inclusion such that they can be easily float up during the processing time. And another thing is that optimum gas stirring also help in the inclusion removal. Optimum gas stirring. Optimum gas stirring, how it is done? That is the gas stirring, obviously what happens, the inclusion will move along with the gas. Most of the cases the inclusion will be entrained. They may not have the relative velocity with respect to the liquid unless they become very big. So most of the time the liquid will be entrained into the liquid stream, or it will follow the streamline of the liquid, because they will be entrained into the liquid, all this moving liquid, that is the impurities will be entrained into the moving liquids and they will follow the path of streamline. So the liquid, that is the impurity, will move with the inclusion and they will reach the surface, right. So think is that it will be like this. If you see the, if you have, usually you have a bath setting from the bottom. So what you have a bubble plume is there like this. This is the bubble plume, and you have this type of circulation. This type of circulation is there. So impurity, what will happen? Impurity will move with the, this impurity will, this is the impurity, suppose here it will move along with the path, and then here you have suppose some slag is there. So then this impurity, when it comes here, it can be engulfed or absorbed by the slag, and then now this velocity is very important. This velocity is important, that is that at which it is coming. If the velocity is very high, in that case inclusion may not be released into the slag, because it will have so much inertia, the inclusion have so much inertia, it will not be allowed to be absorbed by the slag. So if you have little lesser velocity, that is the when the liquid is moving, if they have lesser velocity, then the liquid, the impurity can be released into the slag. Okay. So thing is that if you have a very high velocity, then the inclusion can be entrained. That is this is the liquid are coming like this, so inclusion may remain entrained into the liquid. That is, inclusion may not escape to the slag. So you have to have a optimum velocity, because if the velocity is very high, then also the inclusion will be again re-entrained into the liquid rather than releasing into the slag. But if their liquid velocity is not very high, then the impurity will travel with the liquid streamline, and then when they reach the slag, they will be entrained into the slag, and then that is the way. So that is the starting helps in inclusion removal, because inclusions are entrained into the liquid still, moving still, and they move to the surface and then they move into the slag. Okay. So optimum gas agitation helps in the inclusion removal, but not your very high agitation, right? Okay. So another thing is that liquid product of deoxidation is helpful. Liquid product of deoxidation, because if the product of deoxidation is liquid, they have a coalescence tendency, and as a result, they can form a bigger inclusion. So that's why the product of deoxidation is liquid that are helpful, because the liquid inclusions try to coalesce and form a bigger ones. That's why your silicomanganese, sometimes silicon and manganese, SiMn is used. SiO plus MnO, if your solidification product is SiO and MnO, SiO2 and MnO, they form a liquid product of deoxidation. That's why silicomanganese, that is the SiMn, silicomanganese is used as an deoxidation product, okay, as a deoxidant. So when silicomanganese is used as a deoxidant, they form a SiO2MnO, which forms a product, a liquid product of deoxidation, and they coalesce and make a bigger inclusion and flow type of the system. That's why silicomanganese, SiMn, is used as deoxidant, very helpful from kinetic point of view. So liquid inclusion coalesce from bigger inclusion and flow type, and usually silicomanganese is used, SiMn is used as a deoxidant, and from kinetic point of view, this is a very good deoxidant. Okay, so I have discussed up to this, and I will cover the next part in a next lecture. Okay, the same lecture will be continue, and I will cover it into the next lecture. Thank you very much.